Something is wrong with the outer solar system. It has been wrong for almost 200 years, quietly, persistently, in a way that astronomers, for most of that time, could not quite see. There is a region beyond Neptune, a vast, frozen field of small icy worlds called the Kuiper Belt, where the rules of gravity seem, just slightly, to bend. Where small bodies follow paths they should not follow. Where orbits cluster in ways that, by any reasonable calculation, ought to be random. For a long time, no one knew why. Tonight, we drift outward from the warm inner planets, past Mars, past Jupiter, past Saturn, past the rings, past Uranus, past Neptune, far past Neptune, into the cold, quiet edge of our solar system, into a place where, perhaps, a ninth planet is hiding. Its name, for now, is Planet 9. We have never seen it. No telescope has caught it. No spacecraft has approached it. We do not know its color. We do not know its surface. We do not even know with certainty that it is there. But the mathematics suggests it must be, or something must be. Something with enough gravity to pull at the smallest, most distant worlds. Something hidden in the deep dark, beyond the reach of our brightest cameras. Welcome to Sleeping Galaxy. This is not a story about a place we have visited. It is a story about a place we are still searching for. A quiet investigation in the slow and patient light of telescopes into the question of whether our solar system is exactly what we thought, or whether all this time there has been a ninth member. We will trace the first faint signs that something was wrong. We will follow the work of two astronomers in California who proposed an answer. We will examine the evidence slowly, gently, and weigh it. We will consider the doubts of those who disagree. And we will look toward the great new telescope, now searching the southern sky, that may soon end the mystery, one way or the other. So close your eyes, if you wish, or look up into the deep south of the sky, toward the constellation where Planet 9, if it exists, is thought to be hiding tonight. The night is long. The cosmos keeps its secrets gently, and tonight we search. The first clue arrived quietly in 2014. It came not from a great discovery, but from a small statistical pattern, the kind of thing that, in astronomy, is easy to miss, easy to dismiss, easy to explain away as coincidence. A former student of Caltech named Chad Trujillo was working at the Gemini Observatory in Hawaii. With his colleague, Scott Sheppard, of the Carnegie Institution for Science, he had spent years searching for distant objects in the outer reaches of our solar system. Small worlds, dwarf planets, faint icy bodies in the great frozen field beyond Neptune. By that year, they had cataloged 13 of the most distant such objects, tiny worlds drifting in orbits that take them many billions of kilometers from the Sun. Worlds so far away that their orbits last for thousands or tens of thousands of years. When Trujillo and Sheppard looked at those 13 objects, they noticed something strange. The orbits, they realized, were not random. Most things in the solar system orbit the Sun in patterns that, while not identical, are scattered widely. A planet here, drifting through a particular orientation. An asteroid there, going a different direction. A comet on a third path entirely. The total picture, when you map it all out, is a kind of organized chaos. 8 planets in roughly the same flat plane, but everything beyond them moving in many directions. The most distant Kuiper Belt objects, however, these 13, all with their closest approaches to the Sun far past Neptune, were not scattered. They were clustered. Their orbits, when drawn on paper, all pointed in the same general direction. Their nearest approaches to the Sun were all on one side. Their tilts, relative to the plane of the solar system, all leaned the same way. It was, in a word, suspicious. By the laws of probability, this pattern should not exist. If these objects had been thrown into their distant orbits randomly by passing stars, by the slow gravitational dance of the outer solar system by chance, they should be scattered in every direction, not gathered in a tight, narrow grouping. Trujillo and Sheppard wrote up their observations. They published their paper. They noted, carefully, that the clustering might be statistical bad luck, a small sample, a pattern that would disappear when more objects were found. But they also suggested, gently, another possibility, that something out there, something they had not yet seen, was holding the orbits in place. Something with enough gravity to keep these 13 worlds aligned. Some great unseen body sitting in the deep dark beyond Neptune, herding the smallest objects of the solar system into a quiet, suspicious order. They did not know what it was. They could not see it. But the mathematics, they said, was hard to ignore. For 2 years, that paper sat in the literature. Most astronomers read it, nodded, and moved on. Statistical patterns in small samples come and go. Coincidences happen. The solar system has many quirks. There was no need yet to imagine an undiscovered planet. But there were 2 astronomers at the California Institute of Technology who did not move on. Their names were Konstantin Batygin and Mike Brown. Brown, in particular, was a familiar figure in the outer solar system. He had spent his career searching for distant icy worlds. He had discovered Eris, the dwarf planet whose discovery in 2005 eventually led to the demotion of Pluto. He had, in some circles, been the man who killed a planet. He was, in his own way, the most experienced planet hunter in the world. Batygin was younger, a planetary scientist, a theorist, the kind of astronomer who liked to take observational puzzles and run them through mathematical models until the universe gave up its answer. The 2 of them, in 2015, decided to look more closely at the clustering Trujillo and Sheppard had described. They did not set out, at first, to find a new planet. They set out, instead, to debunk the suggestion, to show that the pattern could be explained without invoking some hidden, undiscovered world, to find a quieter, more conservative answer. What they found, instead, over the course of many months, was the opposite. The more they looked, the more the clustering refused to go away. The more they tried to explain it with passing stars, with the gravity of the Milky Way itself, with the collective tug of the small bodies on each other, the more those explanations failed. The only thing that consistently produced the observed clustering in their computer simulations was a single hidden planet, a planet far out beyond Neptune, a planet roughly 10 times the mass of Earth, a planet on a long elliptical orbit, taking somewhere between 10,000 and 20,000 years to complete a single circle of the Sun. A planet they had not seen, a planet no one had seen. In January of 2016, Batygin and Brown published their paper. They called it, with care, only a hypothesis, but the world began calling it Planet 9. Imagine for a moment that you are trying to understand the motion of a tiny pebble. It is rolling slowly across a large flat table. You cannot see what is pushing it. You cannot see the surface beneath it. You can only see the pebble and the path it traces. If the pebble moves in a straight line, your conclusion is simple. There is nothing in its way, no forces, no obstacles. The path is clean. But if the pebble curves, if it bends gently towards some point on the table, you can begin to reason about what might be causing the curve. Perhaps the table is tilted. Perhaps there's a small magnet beneath the surface. Perhaps, hidden by the tablecloth, there is a heavier object exerting a gentle pull. You cannot see the cause, but the path of the pebble gives you a kind of evidence, a trail of curves, a pattern that points gently towards something you cannot see. This is, in essence, how Batygin and Brown have been searching for Planet 9. They cannot see the planet. They have no direct observation of it. But the small icy worlds in the distant Kuiper Belt, those tiny pebbles drifting through the outermost reaches of the solar system, are tracing paths that, when examined carefully, do not quite make sense on their own. The paths curve in ways that by all reasonable physics should not happen by chance. Something, somewhere, is bending the trails. In their 2016 paper, and in the many follow-up studies that came after, Batygin and Brown laid out the case. They identified 6 trans-Neptunian objects, small worlds far beyond Neptune, whose orbits showed 3 suspicious features at once. First, their orbits all pointed in roughly the same direction. The closest approach to the Sun for each of these 6 objects was on the same side. Second, their orbits all tilted in the same way. Relative to the plane of the 8 major planets, all 6 were inclined at roughly 30 degrees in the same direction. And third, perhaps most strangely, there was a small group of other Kuiper Belt objects whose orbits ran in the opposite direction, orbiting backwards, in a sense, against the flow of everything else. Each of these features, on its own, could be a coincidence. Together, they were not. The astronomers ran their computer simulations. They tried to recreate the observed pattern without invoking any hidden planet. They tried adding the gravity of nearby stars passing through the galaxy. They tried modeling the gentle pull of the entire Milky Way. They tried letting the small bodies in the Kuiper Belt influence each other altogether by the collected weight of their own tiny gravities. Nothing worked. None of these explanations produced the observed clustering. None of them alone could herd the orbits into the pattern that the data showed. Only one model consistently produced the right answer: a single hidden planet far out beyond Neptune on its own long elliptical orbit, anti-aligned with the orbits of the small objects it was shepherding. When Batygin and Brown ran that simulation, the small objects in their computer model fell naturally into exactly the clustering that real astronomers had observed in the sky. From this, they could begin to estimate what Planet 9 must be like. It is large, perhaps 5 to 10 times the mass of Earth, a sub-Neptune in the language of planetary science. Big enough to qualify as a planet by any definition, but smaller than Uranus or Neptune themselves. It is far. Its average distance from the Sun is something like 400 to 800 times Earth's distance from the Sun. At its closest approach, it might come as near as 200 times Earth's distance. At its farthest, it might wander out past 1,000. For comparison, Neptune sits at 30 times Earth's distance. Planet 9 if it exists, lives in a region of space 10 to 30 times further out than any other known planet. It is slow. A single orbit takes perhaps 10,000 years, 20,000, maybe more. The planet, if it is real, was at the same point in its orbit last when humans had not yet invented agriculture. It will return to that point only thousands of years from now. It is cold, so far from the sun that any sunlight reaching its surface is dim almost beyond imagination. The sun, from Planet 9, would look only a little brighter than the brightest star in our night sky. The world itself, if it has a surface, sits in a deep, eternal twilight. Temperatures in models suggest something around 50 Kelvin, about minus 220 degrees Celsius, cold enough that water, methane, nitrogen, all would be frozen rock hard. And, perhaps most strangely, it is dark. Most planets far from the sun still reflect a little of its light back toward us. That is how Pluto was discovered. That is how Eris and Sedna and the other dwarf planets of the outer solar system have been found. They are small and faint, but they shine faintly against the deep black of space. Planet 9, if it exists, may be too faint even for that, too distant, too dark. The reflected light from the sun, by the time it reached Earth, would be roughly 1 trillion times fainter than direct sunlight, almost imperceptible, hidden in the great noise of the deep sky behind the millions of foreground stars. This is why, in the 10 years since Batygin and Brown made their proposal, no telescope has yet caught the planet directly. It is not that we have not looked. It is that, if it is there, it sits at the very edge of what our instruments can see, a mathematical ghost, a planet that exists, perhaps, only in equations, a great cold world drifting somewhere out in the deep dark, never seen, but felt gently in the orbits of the small things around it. That, at least, is the case for Planet 9, but not everyone is convinced. It is important in any quiet investigation to listen to those who disagree. Not every astronomer believes in Planet 9. There are careful, thoughtful scientists who have spent years examining the same evidence Batygin and Brown gathered, and have come to different conclusions. Their doubts are not noise. They are part of the search. They are, in some sense, the slow, gentle pressure that science requires before a hypothesis can become a fact. Let us listen to them for a while. The first doubt is about the data itself. When Trujillo and Sheppard first noticed the clustering of distant Kuiper Belt objects, they were working with a small sample, 13 objects. Of those, only 6 were eventually used by Batygin and Brown to make the strongest part of their case. 6? It is, in statistical terms, a very small number from which to draw a very large conclusion. The presence of a hidden planet 10 times the mass of Earth in our own solar system. This is an extraordinary claim, and as astronomers often say, extraordinary claims require extraordinary evidence. 6 aligned orbits, some critics argue, is not extraordinary. It is suggestive, it is interesting, but it is not yet proof. There is also perhaps a problem with how those objects were found in the first place. Astronomers do not search the entire sky equally. They use specific telescopes, looking in specific directions at specific times of year. A telescope in Hawaii sees one part of the sky most often. A telescope in Chile sees another. The patches of sky most carefully searched are not random. They reflect the locations and schedules of the world's observatories. This means that the small, distant Kuiper Belt objects we have cataloged so far are not a random sample of all such objects. They are a biased sample, skewed toward the directions our telescopes happen to look. If the most searched regions of sky happen to coincide with one side of the solar system, then any objects found will appear to cluster in that direction, not because they really cluster, but because we only search there. This is called observational bias, and several teams of astronomers since 2016 have argued that the apparent clustering of distant Kuiper Belt objects can be explained, at least in part, by exactly this kind of bias. We see clustering because we looked in a clustered way. The real distribution of distant objects, if we could survey the entire sky uniformly, might be perfectly random after all. If the clustering is not real, then Planet 9, at least as proposed by Batygin and Brown, has no evidence supporting it. This is a serious objection. It is hard to fully answer with the data we have. We need more objects. We need a survey that covers the whole sky evenly with the same depth of sensitivity. Until then, the question of observational bias hangs over the entire hypothesis. The second doubt is about alternatives. Even if the clustering is real, even if the distant Kuiper Belt objects really do prefer to point in the same direction, does a single hidden planet have to be the explanation? Several other ideas have been proposed. One suggestion involves the collective gravity of the Kuiper Belt itself. There are many small bodies out there, many trans-Neptunian objects, many faint icy worlds drifting in long orbits. Their individual masses are small, but their combined mass, summed over a great region of space, is not nothing. What if the gentle, distributed gravity of all those small bodies acting on each other over millions of years has slowly herded their orbits into the patterns we see? No single hidden planet, just the collective, patient pull of an entire frozen field. Some simulations have suggested that this kind of mass distribution, if it really exists, could produce orbital clustering similar to what we observe. The proposal does not require any new, undetected world. It only requires that the Kuiper Belt contain more mass than we currently estimate. Another suggestion involves the early history of the solar system itself. 4.5 billion years ago, when the planets were still forming, our solar system was a chaotic place. Planets migrated. Smaller bodies were thrown around. The orbits of objects in the outer regions were shaped violently by close encounters with the giant planets. Perhaps the patterns we see today, the clustering, the tilt, the strange orbits, are leftover features of that ancient chaos, imprinted long ago, frozen now into orbits that no one is currently shaping. No planet required, only a long memory of how the solar system was born. There have been other ideas too. A primordial black hole, the size of a baseball but the mass of a small planet, drifting somewhere in the outer solar system. A distant rogue star having flown by long ago and altered the orbits of small bodies. Even in some speculative models, a fifth giant planet that was ejected during the early solar system and is no longer present, but whose gravitational fingerprints still remain. Each of these alternatives has its supporters. Each has its weaknesses. None has been proven. But each, in its own way, offers a different explanation for the same observed pattern, without requiring a new hidden world. The third doubt is about formation. How would Planet 9 have gotten where it is? When the solar system formed, planets condensed out of a disk of gas and dust surrounding the young sun. That disk extended outward for some distance, but it had limits. The further from the sun, the less material there was. The harder it became for a planet to form. By the time you reached the distance, Planet 9 would supposedly occupy many hundreds of times Earth's distance from the Sun. There should have been almost nothing for a planet to be made from. So, how did it get there? There are possible answers. Perhaps Planet 9 formed closer to the Sun, near where Uranus and Neptune sit today, and was thrown outward by gravitational interactions with the other giant planets. Perhaps it formed far away, in a denser early disk than we currently model. Perhaps it was, originally, a planet of another star, captured by our Sun in a close passing encounter many billions of years ago. None of these scenarios is impossible, but none of them is straightforward. Each requires a sequence of events that, while plausible, is not what our standard models of solar system formation predict. A hidden planet would be wonderful. It would also, in some sense, force us to revise our understanding of how solar systems are built. So, where does this leave us? It leaves us in a state of suspended judgment, a position that perhaps you have come to recognize as you drift slowly through these episodes of cosmic uncertainty. The data suggests something is happening in the outer solar system. The mathematics suggests a planet might explain it best. The alternatives suggest other explanations are possible. The doubts suggest we do not yet have enough evidence to decide. This is, in many ways, the actual state of much of science, not a settled answer, not a confident conclusion, just a careful, slow, patient gathering of evidence, and a willingness to wait. We are still waiting, but the waiting soon may end. In the years since the original proposal, the search has continued. Astronomers have looked with patience in many directions. They have cataloged new distant objects. They have refined their simulations. They have measured the same orbits again and again with greater precision. They have argued with each other in conference rooms and in journal pages, slowly building the case for and against. And in 2024, a new study was published. Mike Brown and Konstantin Batygin have been working on it for years. By this point, they had moved beyond the original 6 objects. The number of known distant Kuiper Belt bodies, the ones whose orbits could be used to test the Planet 9 hypothesis, had grown. In their new analysis, they examined 17 trans-Neptunian objects, not 6, 17. Each of these 17 had a bizarre feature. Their closest approaches to the Sun reach as near as the orbit of Jupiter. This is, on its own, a strange thing for a distant Kuiper Belt object to do. These bodies, drifting at the very edge of the solar system, should not, in a normal arrangement, come anywhere near the inner planets. Objects whose orbits cross Neptune's path tend to get ejected over time, thrown out of the solar system entirely by the gentle pull of the great ice giant. They should not still be there. And yet, these 17 objects are there. With their long orbits and their close passes through the inner solar system, they should not exist on these paths. Something must be holding them in place. Something must, in some way, be repeatedly nudging them. Batygin and Brown ran their simulations again. They tried, once more, to recreate the observed orbits without Planet 9. They tried passing stars. They tried galactic tides. They tried the collective influence of the Kuiper Belt itself. None of these worked. Only when they included a planet, roughly the size and mass and orbit they had proposed in 2016, did the simulations match the observations. The strongest statistical evidence yet that Planet 9 is really out there, Batygin said when the paper was published. Mike Brown was even more direct. In a public statement, he said simply and quietly, "I think it is very unlikely that Planet 9 does not exist." This is a careful way of saying he is now convinced. After 8 years of work, after many rounds of doubt, after many alternative explanations were proposed and tested, after many failed attempts to make the data behave without invoking a hidden world. Brown, the man who once helped end Pluto's status as a planet, who has spent his career being skeptical of new planets in the outer solar system, now believes there is a 9th one out there. There is also, in the years since 2016, a steadily growing list of related observations, other strange features of the outer solar system, which Planet 9, if it exists, would explain. The orbits of objects orbiting backwards against the flow of everything else. The puzzling distribution of small worlds whose orbits tilt far away from the plane of the planets. The handful of objects that travel far above or far below the disk of the solar system on paths that should not be stable over billions of years. Each of these, individually, might have a separate explanation, but all of them together, the clustering, the tilts, the backward orbits, the long-period objects, the objects diving inward from the cold dark, are difficult to explain without a hidden planet. The total weight of evidence by 2024 was beginning to feel substantial. But evidence in science is not enough. We need to see the planet. For 10 years, astronomers have been trying. Several of the world's most powerful surveys have looked methodically in the regions of sky where Planet 9, if it exists, should be hiding. Mike Brown himself, with his colleagues, has spent many telescope nights doing exactly this kind of search. They have cataloged thousands of faint objects in the patches of sky where the planet is most likely to be. None of them has turned out to be the planet. Why have we not yet seen it? The answer is simple and patient. The sky is large. Planet 9, if it exists, is faint. Its likely position is uncertain. Astronomers can estimate the general region, but not the precise location. It might be sitting against a backdrop of millions of foreground stars, indistinguishable from any of them except by its slow motion across many years. Finding it is like searching for a single dim candle in a vast, crowded city by walking the streets one at a time. This kind of search is slow. It is also, with current telescopes, near the limit of what is possible. To detect Planet 9, an instrument would need to be very sensitive, very wide field, and able to image the entire searchable sky many times. Looking for a small object that moves just slightly from one observation to the next. We have not had such a telescope until now. High in the Andes of central Chile, on a mountaintop named Cerro Pachón, sits a telescope that is going to change the search. Its name is the Vera C. Rubin Observatory. It is named after the American astronomer Vera Rubin, whose careful measurements of the rotation of galaxies in the 1970s gave humanity our first strong evidence of dark matter. The observatory is new. it is enormous. And, more importantly, for our story, it is exactly the kind of instrument needed to find Planet 9. At its heart sits a camera, the largest digital camera ever built, 3,200 megapixels, heavy enough to weigh roughly the same as a small car, sensitive enough to detect objects that are almost incomprehensibly faint. In May of 2024, that camera was carefully driven up the Chilean mountain road to its final home, set in place, aligned, tested. The telescope itself is large, but in some sense ordinary. What makes the Rubin Observatory special is what it is going to do with that great camera. Beginning in late 2025, the telescope will start taking pictures of the entire visible southern sky. Not in one survey, in many. Every few nights, the same patches of sky will be photographed again, and again, and again, for 10 years. Astronomers call this the Legacy Survey of Space and Time. They sometimes shorten it, with some affection, to LSST. Most things in the sky do not move. The distant stars, the galaxies, the nebulae, over the course of a few nights, they appear in exactly the same place each time. But objects in our own solar system do move. The closer they are, the more they move. A nearby asteroid shifts noticeably from night to night. A distant Kuiper Belt object moves more slowly, but over weeks and months, even those drift across the field of view. Planet 9, if it exists, would move very slowly. Its enormous orbit means it travels through the sky at a glacial pace. A few arc seconds, perhaps, over months. But Rubin will see it, eventually, if it is there. The same patch of sky, observed many times, a faint dim point, slightly shifted from one observation to the next, detectable by careful comparison against the unmoving background. Astronomers expect that Rubin will, in its first year or two of operation, either find Planet 9 or rule out a very large portion of the sky where Planet 9 could be hiding. Either way, the question is approaching an answer. After 10 years of waiting, after 8 years of mounting evidence, after a century of suspicions about strange motions in the outer solar system, we are close. If Planet 9 is found, it will be one of the great discoveries of the 21st century. The first new planet of our own solar system in nearly 200 years. Since the discovery of Neptune in 1846, no one has ever added a planet to the list of major bodies orbiting our Sun. Pluto, demoted in 2006, was never quite a planet by modern standards. To find a real, true ninth planet, bigger than Earth, far out beyond Neptune, hidden all this time, would be a quiet wonder. It would, in some sense, change how we feel about our solar system. We have lived, for most of human history, with 8 known planets. Some children have grown up with 9, then back to 8. To return to 9 with a new and stranger world out at the very edge of the dark would feel, perhaps, like meeting a member of the family we had never known existed. There is also the other possibility. Rubin may search the regions where Planet 9 should be and find nothing. This is not a small thing. After many years of careful searching with the most powerful survey telescope ever built, the absence of detection would be its own kind of evidence. If the planet is not in the regions where models predict, if it is not in any of the most likely locations, then the case for its existence becomes much weaker. The clustering of distant Kuiper Belt objects would still need to be explained, but it would have to be explained without Planet 9, perhaps by observational bias, perhaps by Kuiper Belt mass distribution, perhaps by some quirk of solar system history that we have not yet imagined. And the long search would, in some sense, end, not with the discovery of a new world, but with the quiet acknowledgement that we had been searching for something that was not there. Either outcome would teach us something. The cosmos is patient with our questions. It does not always answer them in the way we hope, but it usually answers them eventually if we are willing to look long enough. For now, tonight, Planet 9 remains a quiet ghost, somewhere out there, perhaps, drifting in a long elliptical orbit on the very edge of the solar system. Cold, dark, slow, a great frozen world that, if it exists, has been part of our solar family all along, even when we did not know it. Or perhaps instead, the outer solar system is exactly what it seems: 8 planets, a scattered field of small, icy bodies, a few statistical patterns that look meaningful but are not. No hidden world, no ninth member. We do not yet know, but we are looking. The telescope is built, the camera is in place, the sky is being mapped, and somewhere in the coming years, the question that astronomers have been asking for a decade will quietly be answered. The cosmos is patient, the search is gentle, and the night is long. The night is quiet now. Somewhere, perhaps, in the deep dark of the outer solar system, a frozen world is drifting on its long, slow orbit. A world we have never seen, a world we cannot yet name, a world that, if it exists, has been part of our solar family for 4.5 billion years, quietly tugging at the orbits of small icy bodies, leaving faint mathematical fingerprints in the cold edge of our cosmos. Or perhaps not. Perhaps the patterns we have seen are coincidence. Perhaps the orbits of those small worlds are shaped by something else, by the gentle weight of the Kuiper Belt itself, by the memory of an ancient stellar passing, by the early chaotic history of how our solar system was born. Perhaps we have been searching for something that is not there. We do not yet know. The new telescope is watching. The great camera is taking its slow, careful images, night after night, patch after patch of southern sky, looking for a small, dim object that drifts almost imperceptibly from one observation to the next. We are finally close enough to find out, one way or the other. There is something gentle about a question that has not yet been answered, about a search that is still in motion, about a place in the cosmos where the verdict, after a century of suspicion, is still being weighed. If you are still awake, that is all right. The night is long and the search is patient. If you are drifting towards sleep, even better. Somewhere out there, perhaps, a 9th planet is moving slowly through its long orbit. Perhaps it has been waiting all this time to be found. Perhaps not. The cosmos keeps its secrets gently. The telescope is watching, and we search. Sleep well, and good night.